Hello, I am Megan Hickman-Fulk, and my research this summer was on utilizing temporal similarities for improved data reduction. We aim to incorporate time-step information to existing data sampling techniques to yield higher quality resolutions of samples reconstructed post-hoc. Modern-day high-performance computers have increasingly high computation capabilities, allowing scientific applications to produce petabytes of data. For example, the Community Earth System Model climate simulation can produce terabytes of data per day. The Hardware Hybrid Accelerated Cosmology Code simulation can produce up to 220 terabytes of data per snapshot. Due to limitations of the I/O system, these highly detailed simulations are generating data faster than the system can store. The combination of large output data with this I/O bottleneck makes traditional full, high-precision post-hoc analysis and visualization increasingly less viable. There exist data sampling techniques that can save a fraction of the simulation data for post-hoc analysis. With simple random sampling, each data point has an equal chance of being sampled. Each point is considered independently, and a uniform distribution of the data is sampled. These random samples will accurately reflect the original data distribution and will maintain statistical quantities like mean and standard deviation. Here we have the original data visualization, and we can see in this figure that each value has an equal opportunity of being chosen. While this sampling method does save some space, such that we can export the data, reconstruct, and analyze it later, the quality of the reconstructed data is not as high as it could be. There exist some sophisticated data sampling techniques that target important regions of a dataset. For example, this method utilizes data value histograms to create an acceptance function. This works on the notion that rare data values are of more importance to the user, thus they are given a higher probability of being sampled. This figure shows that unlike the random sampling approach, the samples are being clustered around the region of interest. Thus, we can increase the quality in this area. This idea has been shown to give promising results for increasing quality while maintaining the same sample ratio as random sampling. This will be used as the base comparison of our methods. For my summer work, I used the notion that if we combine this spatial sampling technique with temporal sampling, we can enable a higher quality of reconstructed data while using the same data reduction. Here we have two time steps of the Hurricane Isabel pressure variable dataset. Since simulations usually change slowly over time, time steps chronologically close to one another should be very similar in certain regions. If some regions are similar, maybe we do not need to spend the time and space sampling this new time step. Perhaps we can reuse samples from a previous time step. In the following examples, I will continue to use time step 0 as the reference frame, where all blocks are sampled independently of time, as described on the previous slide, and time step 8 will potentially reuse samples from this reference frame. Specifically, if each time step is divided into blocked regions, we can determine if the corresponding previous block is similar or not. If so, we can reuse samples. For example, maybe block 0 did not change very much, so instead of sampling new, we can reuse these previous samples. But for block 58, we can see that the data is changing pretty drastically between the two time steps, so it would need to save samples for this time step independently. So now our question becomes, what determines two regions as similar? One way is to look at the distance between the data value histograms. In this example, I'm using Hellinger distance to quantify the difference between value histograms of corresponding blocks from the two time steps we were analyzing. Here, wherever there is a 0, the data value distributions of corresponding blocks are identical. Since the data values have not changed, the samples for this block will be reused from the reference frame. The disadvantage of this method is the loss of spatial information. By just comparing data values for similarity, we do not know if the values have moved in location, thus potentially introducing error when incorrectly placed samples are reused. If too much error is added, the quality of the reconstructed dataset may be lower than anticipated. A second method for determining similarity is to look at the error between data points. This method considers the data values and locations of a previous sample for a specific block and compares them to the current value at that location. If the root mean squared error for all previous samples is more than the user-specified error threshold, samples will not be reused as they would introduce more error than the user wants to allow. For example, if we set an error threshold of 50, block 0 would not be reused because too much error would be introduced. But the histogram similarity method would have allowed this error because the data values are identical. The disadvantage of the RMSE method is that we need to save the data value and location of all previous samples in order to compare them to the current time step, which takes considerably more space than the histogram method. From the original method, if we choose to reuse samples, we can achieve about the same reconstruction quality while using less space, regardless of similarity metric. In these scenarios, the user specified a space constraint budget that the original method could fill nearly exactly. However, we see the two sample reuse methods do not fill up that budget. Instead of not utilizing that extra space, how might this budget be filled? So we started with two reuse methods that didn't achieve as high of a post-reconstruction quality as the original method, but they use less space. To fill up the space that the users allocated, we choose to add a layer of random sampling on top of the samples gathered thus far. Now each method generates enough new samples such that the same amount of storage is used. Since these sample reuse methods have saved as many new samples as the original time-independent method, and they have access to all of the similar previous samples, they are able to have a reconstruction quality at least similar to or higher than the original method that does not reuse samples. In conclusion, we have combined spatial and temporal data sampling techniques to enable a higher reconstruction quality while circumventing the I/O bandwidth limitations in post-hoc workflows. We've shown that using data value histograms to determine similarity of data regions can be effective, but may introduce too much error due to the loss of spatial information. Overall, using RMSE to determine when to reuse samples will generally always yield a higher quality than the original time-independent method. Our future works include incorporating this into the in situ pipeline such that each time step is sampled and saved as the simulation is running. We also want to test our methods with various datasets to study how they work with different types and different time steps. Thank you.